Alright, so here are some problems from the energy and momentum unit from the openstax textbook. So I'm not gonna do all of them. So here number 7, a shopper pushes a grocery cart, and this is the original problem. It's really straightforward actually. It has 5 questions, but I'm only gonna cover the first one kind of. Shopper pushes a grocery cart this far at a constant speed on level ground against 35 newtons frictional force. He pushes in a direction 25 degrees below the horizontal. What is the work done on the cart by friction? Now, if we look at this one, oh yeah, this one here's different problems. So it says 30 degrees. Also, there's already a force on, but we can use this one here. So this here would be the distance over, and then notice that the friction force, of course, is in the opposite direction, which means the angle between the two is 180 degrees. Cosine of 180 is -1, and that's why we will come up with a negative amount of work. And when we look at, let's see, this would be the problem on homework. So when we look at the solution, there it is. And this, as I said, only the first part here. So we have 35 newtons, which is given in the problem, frictional force times 20 meters times, as I said, the force, the frictional force in the opposite direction, cosine 180 degrees. That equals, of course, 35 times 20 is 700 times a -1, -700 joules. So that amount of work is actually gone. And of course, you would have to put enough force on there, pulling it with the tension in, actually pushing it with the tension in your own muscles, pushing it forward to make up for that frictional force, and then also to put the work into going forward. Now the -700 joules, that's actually work that is gone because friction is a non-conservative force, so that's completely gone. Now the second answer here, as I said on the homework, I actually only covered the first one. But here it asks, what is the work done on the cart by the gravitational force? They actually make a mistake right here. So the formula is correct. Force times distance cosine theta, but the force is downward, which is the weight, and that's not 35 newtons. This here is friction. You know, that's what's given. In fact, there is no mass or weight given, which I put down here in this little note. So whatever that is, maybe it's 100 newtons because it's 10 kilograms, the shopping cart, times 20 meters. But in any case, at the end, it's cosine 90 degrees because the weight is pointing down and the distance is horizontal. Again, I do say that in the footnote down here. So the cosine of 90 degrees is 0, so it still comes out to 0 joules. The third answer here, that's an interesting one because it says, what is the work done on the cart by the shopper? And this one, oh, actually, the interesting one comes later. So in order to make up for the friction force, 35 newtons, the shopper will also have to apply a certain amount of force, which they calculate a little bit later here, the 38.6 newtons, because it's on an angle of 25 degrees. But in order to make up for the 700 joules that are lost due to friction, the shopper would have to put the same amount in, 700 joules, and therefore here the net work being 0, that comes out to a positive 700 joules. When the shopper is done, let me go down a little bit. When the shopper is done actually and keeps pushing, because the cart is going at the same kinetic energy because the speed is constant. So it's the same kinetic energy, which means on the level ground, it doesn't gain any energy. It doesn't lose any energy. Yes, it loses energy due to friction, but the shopper puts it back in due to keep pushing it. And so there's no change in kinetic energy, which means the total network is actually 0 joules. And that's what you see at the end here. The answer in between, that would be because of the angle here, the cosine 25 degrees, because the shopper pushes down. You can see this in this drawing here where this person here pulls on the cart a little bit up. So yeah, we would have to take into consideration the angle. What's only interesting is the force in the horizontal. So you have to take the force component in the horizontal, which of course is the cosine of that angle. So that's why they come up here with the 38.6 newtons. All right, good enough for this. Give myself a little break. All right, so this is going to be about the Kingfisher. Suppose a 30, excuse me. All right, I'm back. So suppose that throwing out 50-gram kookaburra, a large kingfisher bird, which I put somewhere here, I thought I was with the video, hunting, hovering, and diving for fish. It's not getting a snake in this one here, but in this exercise it does. So I'll scroll down here. There it is. Picks up a snake, small snake, and raises it 2.5 meters from the ground to a branch. How much work did the bird do on the snake? How much work did it do to raise its own center of mass to the branch? So here is the solution, really straightforward. It says actually work, but then they compute the potential energy. However, they're able to do that because work is, I'm going to type this here in the vertical, work is the force of weight times the height. And when you do that, then the force of weight, of course, is mass times gravity times the height. So it's the same thing as the potential energy, hence that equals potential energy. So just multiply the mass, which is given for the snake, 75 grams, converted to kilograms, 0.075 kilograms, times gravity, 9.8, times 2.5 for the height. And notice that they made a slight mistake here. There should be a 0.075, but turns out actually the result is still correct, because when they plugged it in, they actually did it correct. So they actually did, the people who wrote the solution menu, 0.075 times 9.80 times 2.5, and there we go. There's the rounded then, 1.8 joules. So they're right. And then for the bird itself, well, it's the same thing, but put the mass of the bird right here. So 0.350 kilograms, and then round to 2 sig fig, 8.6 joules. And that's actually it. All right, next one with a little break here. All right, so let's see. Let's look at the problem here. How long will it take in car? And then the original problem is, where'd it go? Skia. There it is. With a useful power output of 40 horsepower to reach a speed of 15 meters per second, which is about 30 miles per hour, neglecting friction, typical physics problem, right? Neglect friction. How long will this acceleration take if the car also climbs a 3-meter high hill in the process? So the hill is really small, it's 10 feet, so it's kind of like a bump in the road. So I think I put some, maybe this is, I guess I just put that video there, how to accelerate in a car smoothly and safely, beginner driver's lesson. Okay, so the power equation, you usually find it this way in the book. Power equals work divided by time, or energy divided by time. I look at it as that as you climb upstairs in a certain amount of time, at the top you put this much work into it, which is then the potential energy that you have on top of it. So it's easy to calculate mass times gravity times height. And you divide that by the time it took you to get up the stairs. And now, as far as the energy is concerned that you have on top of the stairs, it doesn't matter how fast you went up there. The energy is the same because you have the same potential energy up there. You have to put the same amount of work in. But the power is going to be different depending on how fast I'm going to go up the stairs, if I just walk nicely up, or if I run up the stairs. Then, of course, when I run up the stairs, I put much more power into that. But, of course, it got the same amount of work. So that's the way I explain power. In any case, power equals work divided by time. And here, they actually use the other two forms of it. It's an algebra step away, so work equals power times time. Respectively, time equals work divided by power. And here, my example that I just did in midair was talking about stairs and mass times gravity times height. But here, of course, it's a car that gains speed, so they do kinetic energy, 1/2 mass velocity squared divided by the given power. And let's see, there is, for the power, there is the conversion here. So it says that 40 horsepowers, with 1 horsepower being 746 watts. So 740 times 40. That means a total power of 29,000. What did I do? Oh, 746. Just a little bit off here. There we go. That's the 29,840 watts that they had. And then after the acceleration phase, this is how much kinetic energy the car has. So 0.5 times the 850 times the 15 meters per second squared, which again is the 30 miles per hour. Enter that, so that's 95,625. That's the amount of energy it had to gain, that's joules. Divide that by the power, the 29,840 watts. And because watts is joules per second, the joules actually divide out, and the second goes to the top. So that's why this one here comes out to seconds, 3.20 seconds. Then it says in the second part that the car is also climbing in a hill, so you have to take that into consideration. So you have to say, okay, 850 kilograms times gravity times the hill is 3 meters up. Enter 24,990. So that's a good fraction of the kinetic energy. So in order to achieve the same kinetic energy, it actually would take longer in order to do that, because it needs some of the work that is being put in from the horsepower, some of the work that's being put in order to actually climb the hill. So less energy would be available to get the kinetic energy, hence it takes more time. And then, so let's see this last answer here, plus the, what did I have earlier? Oh, 95,625. And then divide that by the power again, 29,840. And there's the 4.04 seconds that they came up with. All right, give myself a little break here. All right, so the next problem here, this professional boxer, I put two images here. One of them is these two boxers are fighting for the Olympic gold medal. And then this one here, this is not Mike Tyson, this is Donnie Long, who fought him at some point. It's a really long video. I somehow watched this the other day, 40 minutes long, and I was kind of impressed when Mike Tyson was done with the fight, and knocked out his opponent. He actually went over there and figured out, that they're okay, their opponents. So I thought that was really gracious. All right, anyway, this one here, a professional boxer, and so only part 8. So again, this is another problem that's really straightforward that, of course, I will take quite a while to do. So let me get there. And I'm going to pause because I need to get to a different chapter here. All right, I'm back, hopefully. There we go, and there it is. Professional boxer hits his opponent with a 1,000 Newton horizontal blow that lasts for this much. Calculate the impulse imparted by this blow, and it's basically just force times time. So 1,000 times 0.150 seconds is 150 joules. And when I go to, let's see, the solution, and there it is. So the impulse is force times time, and there it is, the 150, and the unit is going to be kind of strange. So it's Newton seconds, force times time, Newton seconds, and then if you take the newtons apart, which is kilograms times meters per second squared, and then you multiply with another second here from the time, you get kilograms times meters per second, and there's no abbreviation for it. So the impulse or the momentum, they both have the same unit, because the impulse is the change of momentum with nothing else. They have that kind of awkward unit there, kilograms meters per second. Again, no abbreviation for it. Let's see, what else do they do in this problem that I didn't put on homework? What is the opponent's final velocity if his mass is 105 kilograms and he's motionless in midair when struck near the center of mass? So as if there was in midair, maybe there isn't enough friction on his feet, so he's just going to take off, So basically what they're doing here is the impulse then goes all in changing the momentum, which then is mass times the change of velocity. And then one algebra step away, change of velocity is change of momentum, which is, again, is the impulse divided by mass. And, ooh, there's something missing here, right there. Final velocity minus initial velocity, that's correct, but that should be still divided by mass, which they do over here. Let's see. Yeah, that looks a little bit strange here. In any case, he gets the original impulse, 150 kilograms meters per second, divided by the mass of the opponent, 105 kilograms, which is about 230 pounds. And then you have minus the original velocity. I wish there was a minus there, actually. In any case, it's still 0 because he was motionless to begin with. And you divide the two numbers, 150 divided by 105 is 1.43. But then it says, calculate the recoil velocity of the opponent's if hit in this manner, assuming the head does not initially transfer. So actually, I think part C should become before part B. So first, the head is going backward, and then it takes the body along. So when the head is going backward and 10 kilogram head, 20 pounds, our heads are pretty heavy. Yeah, 150 divided by 10 is the 50 meters per second. Again, you subtract actually the original momentum or velocity divided by mass, which is 0 because it's first motionless. So 15 meters per second, we already know that's 30 miles an hour that the head takes off. Fortunately, taking the torso along. And then when it transfers the momentum, the actual speed is about 1.43 meters per second, which is about 5 feet per second. All right, good enough on this problem. All right, and the next one I want to do is this one here. Give myself a little break. All right, so train cars are coupled together by being bumped and so on. So let's look at the original problem. Train cars are coupled together by being bumped into one another. Suppose two loaded train cars are moving toward one another, the first having a mass of 150,000 kilograms and a small velocity, 0.3 meters per second, which is 0.6 miles an hour, and the second having less mass, a little bit less mass, and a velocity in the opposite direction, so they're approaching each other, of 0.12 meters per second, which is about 0.25 miles per hour. And what is their final velocity when they couple together? So let's see, do I have a video here for that? Yeah, I think this is the one, coupling and uncoupling rail cars. These speeds that they give us here really slow. That makes sense. You don't want to slam them into each other. So if you watch this video here, which is also kind of like a safety video on uncoupling rail cars, trains, they go at slow speeds. I have other physics books where they go at quite some speeds, like even if it's just 15 miles per hour, one train getting coupling with the other one, that's a little bit fast. You really want to go slow. So what they come up with here is actually reasonable. By the way, the final answer is going to be 0.25 miles per hour. So let's look at the solution, which I just kind of give away. And what you see here, right here, this would be the typical equation. So you have the momentum of the first plus the momentum of the second, and that total momentum is conserved. And that, of course, is the conservation of momentum. And then after, so before something happens, these are the two momenta. And then after, this would be the momentum after something happened. In this case, they coupled. So that momentum afterwards is the same as the one before. And that, of course, is the conservation of momentum. So afterwards, they both take off together. They couple together. That's why you add the two masses. This doesn't necessarily happen. For example, if you have two billiard balls that are hitting each other, they go off in different directions. Well, they would have separate velocities after the impact. But when something couples together, they're always together here, so they have, after they collide, so they have the same velocity. And it could be like in a car crash, the two cars are taking off together afterwards, so you add the two masses times the final velocity. Or one football player tackling the other one, and the two go off together with the same velocity. So that would be the same equation for these kinds of examples. So the first one here is, the mass times the given velocity plus the mass times the given velocity for the other one. Notice there's the negative. And then divide by the total mass here. And when we do that on the calculator, I mean, you can figure this is what's going to be 150,000 times 0.3 plus 110,000 times negative, I have to pay attention to that, 1.2, that's the numerator. What happened to the 1,000? Well, I'll show you in just a moment. Divided by 150,000 plus, oops, and now I forgot something. parentheses for the denominator. Very important for the denominator. Actually, in this case, it's important for the numerator as well because I'm adding stuff. So the two masses coupled together plus 110,000. So what happened to the thousands? Well, I have thousands in the numerator, I have thousands in the denominator, so the two divide out. So I really saved myself clicking all these zeros here. Okay, I hit enter, and of course I do come fully up with the, I think interesting. What did I do wrong? Why did I come up with a different answer than they did? Oh, yeah. I did make a mistake, didn't I? So second entry, as I was talking about why I'm able to omit the thousands, I did make a mistake. Hold on, let me go back here. 0.12, there it is. That's the right one. There we go. I know I come out with 0.122 meters per second, which is 0.25 miles per hour. So again, they actually couple really slowly. All right, pause. So the next problem is going to be really similar to that. So during an ice show and so on. During an ice show, a skater leaps into the air and is caught by initially stationary other skater. What is the final velocity assuming negligible friction? Typical physics one, negligible friction. And we're on ice too. And at the second skater's original horizontal velocity is 4 meters per second. So that's how she approaches him. Let me see, do I have something there too? The video, yeah, so Canadian pairs figure skaters explain the difficult triple. So I think he catches her at some point and then they go off together and they cover well, which is not part of this problem, but it's kind of a neat video too. I mean, anything ice skating, I guess is. And so this one here basically then is going to be the same thing as before. You have the initial momentum over here before something happens and then the momentum afterwards. And because the two cling together, that's why the two masses are together afterwards times the final velocity. Before, we have the mass times velocity or the momentum of one skater plus the momentum of the other skater. Where's that? Where's M2 V2? Well, turns out the second skater is actually initially stationary is what it says at rest, so that's 0. I just wish they would have written it down there and then they would have said plus 0, and we could see it a little better. So other than that, it's pretty much the same as the one that we just did for the train. All right, so I'm going to plug in these numbers. So numerator, 60 kilograms. This is how fast she is. This is her mass. This is how fast she is moving, 60 times 4, plus, well, his momentum is 0. Here it is. I better edit in there so you can see it. Divide then by the total mass. So 60 plus 75. When they take off together, of course they ought to be slower than when she approached them because he slowed her down catching her and she sped him up being caught by him in motion, and therefore we come up with this 1 point, let's see, is it 3 sig fig? Yeah, 1.78 meters per second. And let's see, that was the last problem I wanted to do. All right, so yes, that is the last problem. Then I overlooked that it has a part B, which I didn't include on the homework, but here it is. So how much kinetic energy is lost? And this one here is interesting by itself. That's why I'm going to do it, because in an inelastic collision, kinetic energy is not conserved. It's actually, some of it is used up in simply the collision. So there's some heat dissipating and there's some noise and so on. In an elastic collision, all the kinetic energy is the same. So inelastic collisions, elastic collisions are the ones with the bumper cars and the billiard balls, or in elementary particle physics like the Compton effect. Inelastic collisions, those are the car crashes and the football players, or here one skater catching the other one, or the mine cart filling coal into it, or the trains coupling, those kinds of things, in which case for both of them the momentum is being conserved. For both of them, inelastic collisions, the total energy is conserved, but only for the elastic one is also the kinetic energy being conserved, while for the inelastic one, some of the kinetic energy is transferred into something else. As I said, usually heat and noise that dissipates, which is what they're doing here. So they're saying, okay, the original kinetic energy is this one over here, and then once they get together, this is the energy of them both together taking off. So I'm going to calculate both of them actually individually, and then we can look at the result here. So the original energy, this would be just her. So 0.5 times 60 kilograms times she approaches him with 4, which is squared, 4 squared. So that's her original energy. Him being stationary, that's his original energy. So 480 plus 0. And then once he catches her, it's 0.5 times the total mass, so 60 plus 75, times the speed, the velocity with which he catches here, which we calculated, 1.7 repeating, I think it was, squared, enter, and 213 joules afterwards. Notice that, yeah, the difference between the two is the negative 267 joules that they lost. And that would be then dissipating as damage to the two bodies. You know, the bones do squeeze a little bit, as well as heat and noise during the collision between the two. Okay, there is a nice calculator here at Hyperphysics that actually shows us this. It's this one here. It's the what's called the inelastic collision calculation. So again, this is Hyperphysics. Most collisions between objects involve the loss of some kinetic energy and are said to be inelastic, so this is one of them. So the total energy is still conserved. It's just that some of the kinetic energy is gone. So here we have the, let's see, 60 kilograms is the first one that's heard approaching. Then his is 75, and then she approaches with a speed of 4. There we go. And now the rest is actually calculated. So 1.78 meters per second. That's, we calculated that. That's how much she's taking off. We calculated this one here, 213 joules after she impacts, 480 joules before he catches her. And then the amount of kinetic energy lost is around 267 joules. And then this one here, these two numbers are interesting. That ratio of kinetic energies before and after the collision, so 44% of the original kinetic energy is actually still there. They're moving off, which means 56% rounded is lost due to heat, damage, noise during the collision. All right, now I'm done.